So here is the lecture from last time, and then I want to spend the remaining maybe 20 minutes to talk about the derivation of the Hoeffding inequality. Okay, so this is part 2 of last lecture, and I want to discuss more on this advanced inequality, Chernoff inequality, and Hoeffding inequality. So what I want to do is to give you a more complete derivation of the results. Okay, so we talk about this two-sided events of a Hoeffding inequality. And so the event that I'm trying to analyze would be this bad event called the nu compared to a good number, which is mu. I want to characterize this bad event being that your random estimate compared to the ground truth is bigger than certain epsilon. So this is called a bad event, and since I have an absolute value, I can break it down into two separate cases. Each one is upper bound by A. And now, this is the main result of the Hoeffding inequality. And we mentioned that this is a much tighter bound than the Chebyshev inequality, which we used to see in the undergraduate textbook. Now, you may ask, how useful is this inequality? This inequality is extremely useful as n and epsilon goes to a big number. Okay. Now, normally epsilon would be a fixed quantity, and then you are growing n. And so as n goes to infinity, then you can see that the right-hand side of this inequality will become 0 very, very rapidly. And so compared to the Chebyshev inequality, we see that this one is decaying much faster, and there is a much tighter bound for the empirical observations. Someone asked, since you have this inequality here, and you're assuming that xn is between 0 and 1, isn't it a very strong assumption that the Chebyshev inequality is not bounded by this? This is true. That it is true that this random variable xn has to be living between 0 and 1. It is a very strong assumption. However, if you look at the bound that it provides is a much better bound. So now you can say that then am I able to relax this constraint to be just a random variable with certain standard deviation, stuff like that, like a Gaussian random variable. So if you have some special choices of the random variables, then you can lift this bound between 0 and 1, and you can still get something very tight. It just will not be the Hoeffding inequality. You can get something else. You can get another set of inequality. So you can even say that all these random variables, they are not bound between 0 and 1, but they're just finite. They're just finite. And then the finite interval could be very big. And then you can say that each random variable, they have their own standard deviation. If you try to do that, you have another set of inequalities to try to characterize. All these, they are under the category called the large deviation analysis or large sample theory. And all these probability inequalities you can find from those materials. So for this course specific, we are only going to look at this Hoeffding inequality because the xn that we are going to worry about in our course will be whether you make a mistake or you haven't made a mistake. It will be 0 and 1. And therefore, this Hoeffding is sufficient for the discussion that we need. So what we are going to show is that the Hoeffding inequality can be derived using two very simple tricks. One is that you can take the e to the both sides of this event. Now we are reducing the absolute value to two cases. So I just need to analyze one case. The other case will just be the symmetric version of this one. And if you look at this inequality, you can see that on the inside the probability, you have this event, and here that will be your empirical average. Okay, so that's a random variable. And then you're taking the e to the power s on both sides of this inequality. Okay, so you're taking this, and now why can you take this? Well, you can take this because e to the power s is an increasing function, and by taking e to the power s, you're not changing the probability of getting that event. So you can do that. And then I can apply the Markov inequality, something that we discussed last time, to set the upper bound on this probability using the ratio of expectation of this event and also this the right-hand side. Then by independence, you can pull the n out, and then you're just analyzing this ratio. And it turns out that this numerator is really just the moment generating function of the underlying random variable that you're analyzing. So you can see that there are the two tricks involved. The first trick is this, that you apply the e to the power s on your two sides of the inequality. And then the second trick is to apply the Markov inequality, because otherwise how can you bound this probability of events? Okay, so then you can see what will happen next. As long as I can find a good upper bound on the moment generating function, which is the numerator of this equation, then I'm pretty much done. So what I want to do next is to comment on how we can find the upper bound of the moment generating function. It turns out that in the literature, there is a thing called the Hoeffding lemma. That's why it's named the entire inequality is named Hoeffding. So in the Hoeffding lemma, what they show is that the moment generating function of this random variable, the random variable is xn minus mu, the moment generating function is upper bounded by this e to the power s squared b minus a squared divided by 8. Okay, where b and a, they are just the upper and lower bound on the random variables. So you can say that you can see that if I'm looking at xn is between 0 and 1, then what will be the upper bound? Well, this upper bound will become e to the power s squared b minus a just 1, right? And then that would be divided by 8. So that is a very simple upper bound on this moment generating function. So you can show that the expectation of e to the power s of xn minus mu, okay, it will be less than or equals to s squared divided by 8. Okay, so that is true as long as your random variable xn is between 0 and 1. And I don't really care about what kind of distribution of xn you have. Okay, it can be any distribution, and this inequality will still hold. Okay, so at this moment, you can see what we are going to do. You can go back to the previous slide, and you can see that previous slide we have this probability, the probability of nu minus mu bigger than epsilon. I show that it is equal to expectation of e to the power s of xn minus mu, and then divide by es of epsilon to the power n. So this is what I get from the previous slide. Okay, and now I know that by the Hoeffding lemma, this quantity is going to be upper bound by s over 8. So it will become e to the power s squared divided by 8 divided by es epsilon, the entire thing take to the power n, right? So because I'm just replacing the numerator by the bound that I'm having. Is that okay? Okay. So and then if you do that, then you can try to do some simplification. So the simplification will be that you can take this e to the power s squared n divided by 8, and then minus e to the power okay, so minus s epsilon n. Okay, so there will be e to the power this entire thing. Okay, because you are taking nth power of the numerator and then taking an nth power to the denominator. So you just multiply them out, and then in the exponential space, you just take the subtraction. Then what do you have? Well, then you have, you can group the terms together. So it would be e to the power of n divided by 8 of s squared, and then n times epsilon times s. Okay, so now you can see that this is a function of s. Okay, so you see that this probability of nu minus mu bigger than epsilon is upper bounded by this quantity, and this has to hold for any s bigger than 0. Is that okay? Okay, so this is just the some calculus of all these equations. So what? Well, so you can see that what we are left with is just to play with this parameter s, because this s is a dummy variable. It somehow is there, but I just don't know what kind of s that I need to choose, right? And this inequality says that the probability will be upper bound by this for whatever s that you give me. Okay? And this for whatever s you give me means that among all these s, some s will be a worse upper bound, and some s will be a tighter upper bound. Right? I can choose the s, make it bigger, make it smaller, move it around. Some will be, for some choices of s, if you think about if you choose s to be 10,000, you put it here, of course this will be a good, it will be a valid upper bound, but it just be overkill, right? Then if you make s equals to 0, then it may not be a legitimate upper bound, okay, it may be too small. So there may be some choices of the s that you need to pick very, very carefully, such that this upper bound will become as tight as possible. Okay? So, let me ask you, what would be the appropriate choice of s that can make this as tight as possible? This question can be answered when you try to solve the following problem. You can say that, so here is e to the power n divided by h of s squared minus n epsilon times s. Okay? And then this is true for all s bigger than 0. Now, I want to find an s, okay, that can minimize this entire quantity. Because it's true for all s, and of course, one of the s that can minimize this entire expression will also be true, because that minimizer is just one of all these possible s's. Okay? So let's say, let s star equals to the arc mean of this thing, right? I'm just saying that among all these possible choices of s, one of those will be the guy that can minimize this upper bound, okay? And if I can find this s star, I haven't found it out yet, but if I can find it out, then this will become the following. You will have this probability. It will be less than or equals to n divided by 8 of s star squared minus n epsilon s star. Okay. Now, of course, if you put an s star here, and then you compare with this of course will be bigger than that. But I'm not saying that. Okay, I'm not saying that this with s star it will be upper bound on here. I'm saying that if you choose the upper bound, if you choose the s star, then the s star will be even smaller. It will be smallest among all the possible upper bounds that you're considering. So then the question goes to what would be the s star. Then you can ask, okay, s star equals to the arc mean of this quantity, right? It will be the arc mean of the exponential of this guy. But exponential is increasing, so I don't really need to worry about the exponential function. So s star is just the arc mean of n divided by 8 of s squared minus n epsilon s, right? Now, can you minimize this function? This function shouldn't be too hard because it's a scalar variable, it's quadratic, minimization of a quadratic equation. How difficult can that be, right? So what do? Well, you do your favorite, taking derivative, set it to 0. So if you take the derivative, set it to 0 of this entire thing, you will get n over 4 of s minus n epsilon. Okay, and then you set it to 0. Okay, so then what do you see? Well, you can see that s will equal to 4 epsilon. Okay, so s equals to 4 epsilon. Okay, so once you have this 4 epsilon, then you can go back. Okay, so now let me go to the next slide. So you can go back to the previous equation. You can ask, okay, then what is the upper bound? So the probability of this event will be upper bound by e to the power n divided by 8 of s star square minus n epsilon s star. Let's just put in your s star being 4 epsilon. Okay, so this is your s star. So you put in the 4 epsilon there, so you have e to the power n divided by 8 of 16 epsilon square minus n epsilon, and then you have 4 epsilon. So then you can simplify the equations. You have e to the power 2n and then epsilon square minus 4 epsilon square n. So then finally we can go to this equation of equal to e to the power minus 2 epsilon square n. Okay, so this probability of this bad event would be upper bounded by this e to the power minus 2 epsilon square n. And then this is only for one side. And now if you consider 2 psi, then it will become 2 times e to the power minus 2 epsilon square n. Okay, so now we go all the way back to the original thing that we want to prove, which is the Hoeffding inequality. You can see that this is indeed what we have in the beginning. So the Hoeffding inequality says that as long as your random variable xn is between 0 and 1, then this probability will be upper bounded by 2 times e to the power minus 2 epsilon square n. And I have just showed you that it is indeed the result. Okay, so what is the take-home message of this entire procedure? I do want to spend some time on this procedure because I think this procedure is very, very general. And it is very, very powerful that you can actually apply to any kinds of random variables. Okay, so today you're studying this random variables with the bound between 0 and 1, and tomorrow you may want to study another set of random variables. But this entire procedure, this recipe procedure, is applicable. This is very general. What do you do? Well, you go back to this E trick. You still do the same E trick here, and then you do the Markov inequality, and then the rest is just to find the upper bound on the moment generating function. Now, for different random variables, you have different moment generating functions, and therefore you have different bounds, and usually the difficulty will go there. But for some well-known distributions, you can easily find good upper bounds in the literature, like this Hoeffding lemma. Okay, it's a very useful lemma that applies to the random variable xn, which is between a and b. Then you can apply that, and then you can get this upper bound. Now, is this a good upper bound? It's pretty tight. Now, can you do even better? If you know more about xn, you can get an even better upper bound on your moment generating function. And once you do that, then the last step of the trick is to solve this minimization problem. Now, realize that this is a very important step because this inequality holds for all s, and therefore you can just choose one s that can minimize this upper bound. And by minimizing this upper bound, you can really get the tightest bound for the probability that you're considering. Okay, so this diagram we have seen before. It is the comparison between the Hoeffding inequality and also the Chebyshev inequality, and we see that the Hoeffding is a lot tighter than the Chebyshev. And we now can understand where does it come from. It comes from all these simple tricks that we introduced, and then it is indeed a much tighter bound as n goes to infinity. Now, I want to emphasize that this tightness holds when n is big. So when you look at this diagram, the tightness happens when you're looking at these events. Okay, here the x-axis is n. As n becomes big, then it is true. If n is extremely small, you're looking at here, and then if you see that the bound is not tight, that's the typical scenario. Okay, the bound is not designed to handle small n. The bound, they are designed to handle very, very large n. Okay, it's an asymptotic result that only applies when n grows. If n doesn't grow, then it doesn't work. An example would be that if you ever try to consider a random variable x1 to xn, and then their variance is not constant, okay, and imagine that the variance is shrinking, then this may not be a good bound. Why? Because as the variance shrinks, then that means as n grows, you have more and more deterministic behavior of your sequence of random variables, and then the bigger n that you have is not going to help you to achieve these asymptotic results. Okay. And so you need to understand that this asymptotic results is really just applying to situations where n is big, and then your random variable, they have some kind of independent structure usually, and usually you want them to have some identical distributions. So IID is usually the thing that you want to assume. But even for cases where ID they are not true, there are results that can still be applied. Okay? It's just a little bit more complicated, especially when you have problems that involving a dependency between the random variables, then Hoeffding is not applicable. Okay? Then you need something else. I mentioned this result last time, and I want to highlight it again because this perspective will be used very often when we introduce the learning theory results. So in learning theory, we sometimes want to look at what is the probability that your random estimate deviates from the ground truth by bigger than epsilon, and you want to bound this probability. But in many cases, we want to write in the equivalent way. We say that with probability at least 1 minus delta, we have this random quantity is bounded by this sandwich inequalities. Now, what does it mean? It means that nu will be your training error. Okay, so nu will be your training error. You want your training error to be within your testing error. Okay, so your testing error is mu, which you don't know. But then you want to make sure that your training error is no bigger than plus or minus epsilon away from the true testing error. So if you can make this epsilon small, then that means your algorithm is doing well. Okay, so you do want to have this kind of statement in your algorithm. Now, if you use the Chebyshev inequality, then you can show that the delta, the probability, will be given by this, and therefore your epsilon will be given by this quantity. So it's scaling with respect to square root of n. And here, you will also scale with respect to 1 over n, square root of 1 over n, but then you also have a log of delta. So as delta goes to an extremely small number, then this epsilon will become very small. So here is an example. For the probability at least 1 minus delta, we have this quantity using the Chebyshev inequality. But if we use the Hoeffding inequality, we can show the same thing, but then the two epsilons become these. So you can ask the following set of questions. I have data sets that contains n data points. I want to estimate the mu. How many data points do I need? Then the other person will say how much delta that you can tolerate. And then the person say, I only have a limited number of data points. How good is my estimate? Then the person can say, how many data points do you have? Right? So you can see that there are a very tight relationship between what? Between n, the number of samples that you have, the tolerance that you will be able to tolerate, and also you want to know the goodness of your estimate. Okay, so epsilon, delta, and n, they're all correlated in this equation. Okay, so let me tell you. If you say that, okay, I want my delta to be 0.01, 1% error, then you put the delta here, then this formula will tell you what is the n that you need in order to make sure that this is well between certain number, right? So vice versa, if you say that I know the fixed number of n, and then I also know the the delta I have, I want to know how good is my estimate, you can just plug this number in and then you can calculate. So to give you some sense of these numbers, this is an example that if you use the Chebyshev inequality, you will get this bound, and then if you use the Hoeffding, you get the set of bounds. Now, if I know delta is 0.01, 1% error in terms of probability, and I know that I have 10,000 samples, and I know that this is a random variable of sigma equals to 1, then you can plug this in, and you can calculate what is the tolerance that you can afford. Okay, so this is the epsilon that you can afford. And you can compare the two. If you use the Hoeffding, then you can, with the same number of training samples, Hoeffding says that the epsilon that you will be able to see will be 1 order of magnitude smaller. Now, this is a lot tighter than the Chebyshev. It's a very, very good prediction of what's happening. Now, if you change the question to say that if I still want to keep 0.01 as my probability of error, and then I change my epsilon to be 0.01, so that means my confidence interval, these two numbers it becomes 0.01, and then I set my sigma equals to 1, then Chebyshev says that you need 1 million samples. And then Hoeffding says you just need 26,000 samples. Okay. Now, which one is correct? Both are correct. This is just an overkill. Okay. So you can see that having a tighter bound actually buys you a lot more information. It says that what is the smallest number of samples that you will need in order to guarantee that your random estimate lies between the confidence interval. Now, this is the smallest you can ever get according to Hoeffding. If you can get an even tighter upper bound, then you may be able to get smaller. Okay. Now, certainly if you go with 1 million, you will be guaranteed to get a good performance, but that's just going to be overkill. Okay. So, when we go to the learning theory, you will be able to see these examples again and again, which we will quantify. All right, what is the number of training samples you need with respect to what is the degree of freedom you have in your model? And then there will be a very nice trade-off between the two, which says that if your model is complex, then obviously you need a lot more training samples. Otherwise, you just cannot learn the entire model. All right, with that, I will stop here, and then I encourage you to take a look at some online materials. You can also try to read this chapter from the book, and then we will not meet in person. However, if you have a question, you can ask me through email or also post questions on Piazza. All right. Okay. Thank you, everyone.